All right, let's dive right into an explainer that's going to completely flip how you view the so-called gold standard of scientific research. If you've spent any time around scientific papers, you already know the magic number, right? 0.05. Hit it, and boom, you're published. Miss it, and your research practically vanishes into thin air. But what if literally everything we've built around this magic number is deeply, fundamentally flawed?
So we're kicking things off with a pretty provocative question today. What if that 0.05 statistical threshold, the one you've been taught to blindly trust as the rock-solid foundation of modern null hypothesis significance testing, was actually just a historical fluke? What if it was just a practical shortcut that somehow, over time, morphed into absolute scientific dogma? That brings us perfectly to our mission today. We are going to systematically tear down and deconstruct the alpha 0.05 standard. We'll trace back to where it actually came from, unpack why relying on it exclusively is fracturing the foundation of modern science, and, most importantly, we're going to help you build a much more stable, modernized framework for statistical inference. Section 1. The origins of 0.05. Believe it or not, the genesis of our modern scientific standard traces all the way back to English agriculture and beer brewing. Yeah, seriously. Back in 1910, Wood and Stratton published a paper in the Journal of Agricultural Science. They just needed a way to protect crop yield recommendations for farmers, so they advised 30-to-1 odds against making a type 1 error. If you run that math, 30-to-1 odds convert exactly to a p-value of 0.0323. That number was eventually just rounded up and baked into statistical tables. Meanwhile, over at the Guinness Brewery in 1908, a guy named W.S. Gossett invented the t-distribution to check probabilities in small batch beer testing. He actually had to publish his work under the fake name Student, just so Guinness's trade secrets wouldn't leak out.
And there's a quote from Wood and Stratton that really grounds this whole thing. They said practical certainty meant enough certainty for a practical farmer. You see, these early statisticians were managing highly practical, immediate economic risks. They just wanted to make sure they didn't recommend a total dud of a crop to a farmer who relied on it to survive. They were absolutely never trying to establish undeniable, absolute scientific truths.
Section 2. Myths of the p-value.
So think about null hypothesis significance testing, or NHST, as a crumbling pillar. It was invented as a risk management tool for crop yields and beer fermentation, remember? Not as this ultimate arbiter of scientific truth. But over the decades, we've treated it like one. And today, that pillar is seriously buckling under the weight of conceptual misunderstandings, methodological instability, and massive systemic failures.
To fix this, we've got to clear away some major myths. P is not the probability that the null hypothesis is true. It is not the probability that your data is just due to chance. And it's definitely not the probability of making a wrong decision. We need to lock in the strict reality here. P is solely the probability of the data you found, assuming the null hypothesis was actually true. That's the whole shebang. Misinterpreting this can totally alter the conclusion of a study, so you've got to commit to this strict definition. Section 3. Cracks in the foundation.
The cracks really start with a fundamentally false premise. The whole system tests against a null hypothesis, the idea that there is absolutely zero difference between two populations. But come on, populations are almost never exactly equal before data is gathered. In reality, finding a difference is practically guaranteed if your sample size is just large enough. The real danger is that NHST forces this dichotomous on or off switch. An effect is either significant or it isn't. But science isn't an on-off switch. The correct path is to turn the dial over to effect size. We shouldn't just be asking, is there a difference? We need to measure the actual magnitude of that difference to see if it even matters in the real world.
To put this into perspective, let's look at a 2014 simulation by Cumming of a two-group comparison where a real difference of 10 actually exists. When you run identical replications, you get this terrifying chaos that Cumming calls the dance of the p-values. They bounce wildly from less than 0.001 all the way up to 0.749. If you're relying purely on the p-value, you only captured the real difference 11 out of 25 times. Now contrast that chaotic dance with the beautiful stability of confidence intervals. They aren't just a simple yes or no, they actually quantify uncertainty. In that exact same simulation, confidence intervals captured the real difference 23 out of 25 times. It's time we stop relying exclusively on p-values, for sure.
Furthermore, we've got two more massive structural flaws to deal with. First, NHST acts like an amnesiac machine. It totally ignores previous results. Every single analysis resets to the exact same starting point, the null hypothesis of no effect. which completely flies in the face of the scientific ideal that knowledge is cumulative. The fix here is Bayesian statistics, which actually accounts for prior knowledge. And second, inferential statistics rest on these totally fragile mathematical assumptions, like perfect normal distributions, that are almost never verified in the real world. Unverified assumptions lead directly to mistaken conclusions. You've got to proactively test your assumptions using software before jumping the gun.
Section 4. The publication bias problem.
Now think about the scientific literature as a giant funnel. Hundreds of well-designed, competently executed experiments are poured into the top every day. But because of this rigid demand that p must be less than 0.05, only the significant results actually pass through the filter and get published. The rest, they get dumped into a massive invisible pile. This creates a truly terrible incentive structure. It encourages researchers to engage in p-hacking, making these conscious or even unconscious data handling decisions just to artificially lower that p-value so their work actually sees the light of day.
So, what's the best way to combat this systemic failure? Pre-registration. This is a real game changer. It means researchers lock in their entire plan, their hypotheses, their sample sizes, the exact data analytic strategies on platforms like the Open Science Framework before they collect a single drop of data. It forces absolute transparency and completely strips away the temptation to manipulate or p-hack the data just to hit some arbitrary threshold.
Section 5. Modern tools for better science.
Now that we know the problems, let's pair those old flaws with their modern fixes. Conceptually, we need to swap out that dichotomous on and off thinking for effect sizes. Methodologically, we've got to replace those super unstable p-values with confidence intervals. And systemically, we need to mandate pre-registration to lock in scientific integrity from day one.
What we're seeing right now is that science is experiencing a natural, necessary, and honestly a very gradual shift. We're slowly declining our exclusive reliance on NHST. Instead, we're increasing utility by looking at effect sizes, quantifying uncertainty, and incorporating prior knowledge. Understanding the accidental origins and the historical limitations of the p-value prepares you to adjust to the future. True meaning is derived from your data by looking through multiple lenses, not by obsessing over a single arbitrary threshold.
I want to leave you with this final thought. Science is all about growth, change, and adapting to better evidence, right? So now that you know the hidden history and the very real limitations of the past, how are you going to adjust your own analytical practices? As we move beyond the accidental standard of 0.05, how will you derive true, multifaceted meaning from your data for the future of science? Think about it. See you next time on The Explainer.